Okay, so ladies and gentlemen, I actually thought I'd begin by a little bit of a retrospective. I actually didn't do a retrospective yesterday, and so we've seen a fair bit since my last one. Within that time, we built up a hierarchical model, a model that captures these multiple levels of context. And models like that afford many benefits to recommend them. We didn't really tap into it, but often one is interested in computing statistics or looking at processes that operate in particular levels of context. So you're interested in understanding the dynamics that apply at different levels of scale. And we know from complex systems that often we'll see quite different behavior at an individual level, a family level, a regional level, for example. And we can capture that in these hierarchical models, these models that include these successive and nested contexts. But they also provide a convenient place for comparing statistics from those models with statistics gained through multi-level analysis, hierarchical linear modeling, mixed effects models, etc., in biostats. So they can be quite helpful for comparing with findings from empirical evidence. Using contemporary statistical methods. It's also a very natural thing to build a model that has these nested levels of scale when you're reasoning about, say, metapopulation. So you have farms, and each farm has on it animals, and the animals move between farms. Or if you're dealing with populations moving between different towns or villages or reserves or what have you. So hierarchical models have a lot to recommend them. We could have, but we didn't, have processes that are characterized using state charts or stocks and flows or other components, events, operating at each of those levels. So we could have had a certain process operating at the city level, having to do with city operations, municipal processes, and that could have been described in the city agent. And we could have had separate dynamics going on at the level of the individual and indeed at the level of the whole system. So models like that are very, very convenient for thinking about the nested context in the world. Okay, and that's why I want to spend some time with them. We also use that model to introduce some features having to do with output from any logic visualization. So we had the histograms and we had the time plots, which we saw that we could, the latter of which, time plots, we could do more or less declaratively. We could say, plot this thing over time where the thing is a value. It's something that computes a value, like a call to a statistic in the population. Now, yesterday we spent... Oh, thanks. Thank you. No worries. So we also went on to characterize a hybrid model, one of our first, where we looked at service-seeking behavior and people's presentations to clinics. So there we had people getting infected from others, and based on their health status, they could elect to present at a clinic. And they would choose the nearest clinic to them and present there. And we saw how we could, more than that, we could add clinics in dynamically and observe the consequences. We created some outputs for common measures, things like the fractional prevalence in the population. And we also had statistics being generated on individual level longitudinal measures, things like how many times a given person had been infected, things that depend on their history. This is not a small matter. If we consider aggregate models, classic ordinary differential equation, compartmental, system dynamics, aggregate models, whatever term you use to describe them, those models give cross-sectional depictions of a population over time. They count at any one time the number of people who are susceptible, exposed, infected, and recovered, for example. But they don't provide us that individual level view of how many times a given person has been infected. So they have difficulty capturing and fully expressing and being compared against patterns we see in the world, patterns involving the things formerly known as frequent flyers. For example, the fact that perhaps 40% of our STI clinic population are people who have reported have come more than 6 times in that year or something like that, which are frequent patterns. We see Pareto effects where sometimes 80% of the users of the service, 20% of the users account for 80% of the needs or what have you. So if we're dealing with populations which are heterogeneous, some people use the service a lot, or some people get infected a lot, and others much less so, it can be very fruitful within our models to capture those sort of patterns at the level of an individual. And it gives us this resolution, this ability to ask about targeted interventions, for example. We can ask, how would effective an intervention be if we focused it on people who, within the past year, have presented at the clinic more than 3 times? Maybe we have different care pathways, perhaps some involving counseling, for example, if a person has been there more than 6 times in the past year. Maybe we want different types of treatment for individuals with different histories. And we can't get that effectively in a general way with an aggregate model. We can get it with an individual-based model. And we saw how we could accumulate statistics on that, the number of times I've been infected. We further, though, saw that we could compute statistics that were not cross-sectional, but were what I would call flow statistics. So they'd be something like the incident case count for the past week. Remember, we put in place some mechanisms so that on a weekly basis we could report the incident case count. Now, that can't be ascertained at any one time, the number of people that have presented over the past week. Instead, AnyLogic didn't provide a great way to capture it. Instead, we had to introduce a variable, the running total of the number of people who have gotten infected in the past week. And then we incremented that variable every time someone got infected. And then at the end of the week, we reported it and we reset it to 0. Boom. And we restarted again. And that's an example of a flow statistic. That's an example of a statistic. It's not cross-sectional, but it's a common need in health, right? We want to know how many people have come to the clinic in the past year or something along those lines. So, and it's not uncommon. We might need to compute that individually. How many times has this person come to the clinic in the past year? So I showed some common needs there by building those mechanisms. Yes, Roberto.
I'm thinking if, for example, patients with complex conditions, and multiple conditions that exacerbate at different times, and could be because of the winter you have a flu that generates acute tachycardia that generates presentation to the hospital.
Sure.
But those events are not registered anywhere in the data. The data, all I know, that person presented 3 times this year, but I don't know why the person presented, or the data is not available.
Right.
So how can I make assumptions about that if I don't know?
Well, maybe I could try to get closer to handling that question in my first lecture of the day, which would be a model conceptualization, where I can make some comments on that. So with your leave, I'll defer that for a little bit of time, okay?
Sure.
But it's a topic which does bear on the conceptualization side, okay? So just trying to wrap up the retrospective here. Then yesterday, beyond the hybrid clinic, we spent the afternoon building up some additional models. And I'm just going to remember for our models built in class, yes, the health economics model. How could I forget? So we took a model that we had built earlier and we layered on top of it some features to capture health economic quantities, things like quality of life measures, which were sensitive to comorbid conditions, and cost sensitive to comorbid conditions. And I went, as is typical in this boot camp, I didn't let myself simply use the very simplest possible case, because I wanted to challenge people, but I wanted to provide tools that will scale fairly well, or that will capture many needs that it's not immediately obvious to someone how you capture them in any logic. So I captured these quality of life and cost measures that could take into account comorbid conditions. And then we used actually a bit of hybrid modeling to build this up in the model by totaling up things like quality of life to be qualities. We integrated up costs to be accumulated costs over time. And we did that in a discounted and undiscounted fashion. And then we layered on top of that some parameter variation experiments, which allowed us, amongst other things, to compute incremental cost and incremental qualities between a baseline and some intervention. And from that, we could compute incremental cost effectiveness ratios. Okay? So in the model, through a parameter variation experiment. But we saw that parameter variation experiments could further be used to capture, to be able to reason about the regularities that a model presents in the context of stochastics, okay? In the context of situations where if we run it once, twice, 3 times with different random number seeds, we get actually rather different results. We want to develop an understanding of the model that's robust in the light of these stochastics. And one of the ways we do that is to build up a parameter variation experiment which summarizes results across many realizations. And so we introduced a histogram 2D object that characterized a model's results with respect to one particular outcome measure across many realizations. Remember, that was that thing where we had have bands, and the ones that were darker indicated that many runs went through that place. So it's dividing up a 2D histogram. It's kind of like dividing up a space like this. So we might have time on the x-axis and some outcome on the y-axis, and it's divided up into bins both horizontally for times and vertically for values. And there's all these, there's a grid of bins, and we're counting the number of times the trajectory goes through that bin. We're incrementing it. So if you slice it at any given time, what you'd see is a histogram for that time about where the trajectories went at that point in time. If you were to slice it at one time, you'd get a count for different values of the y-axis, say the number of people infected at that time. You would get a count of how many trajectories that number fell within this range, or within this range, or within this range. And so you might see a peak where many trajectories tended to cluster, but then some outliers on the tails. That would be in a 2D histogram. If you slice it by time, you'd see a histogram. And so we had these 2D histograms that we introduced to summarize model results over many runs. And that could help us understand the degree of variability we see in those runs. Now, what I didn't show, I asked you to probe a setting. Nay, I asked you to tweak a setting that asked you to whether you want to summarize envelopes or bins. And I asked you to set it to bins. That creates that 2D histogram. You could have done envelopes, and the envelopes would have presented quantiles or fractiles. In other words, around the median, they would delineate envelopes where successively larger fractions of all runs fell. So, 50% of all runs fall within this range around the median. 75% fall within this range. 97.5% fall within this range. That's what envelopes would have given you. But on. Wow, it was long yesterday. I thought we'd cover less, but we actually went on to do parameter variation experiments for varying the values of parameters. And we saw that we could use that same histogram 2D mechanism to summarize how a model responds as we change assumptions about parameter values. So we could run the model with different assumptions about parameter values, either drawn from a distribution in a Monte Carlo sort of way, or by systematically increasing the value of that parameter. One parameter or several. We could explore as this parameter goes up in these steps and that parameter in that step. Conceptually, we're exploring a whole grid of parameter values. How does the model change? Results change with respect to certain outcomes. And we saw once again that histogram 2D could be used to examine that.
I assume
Yes.
you could then, like after that, we looked at calibration and optimization for the calibration.
Yeah.
I assume that you can put the optimization step over the parameter step in that case.
So they're closely related. I'll talk about that.
So
Okay.
you can't run that.
So
Optimization
so this is a good question. So let me I'll address your question in a let me circle around and then address it. Okay. So parameter variation departed from our previous runs of models in the sense that one experiment, ladies and gentlemen, it used to be through most of this course till yesterday, one experiment ran the model one time. All right, you would run this experiment and it would fire up main, run the model, extract some output, show some output, and that's that. Now, starting yesterday with parameter variation, a given parameter variation experiment could run the model 10 times, 100 times, 1,000 times, over and over and over again. It could run it for different assumptions about the parameters, or it could run it just with the same parameter values, but just take into account stochastics, right? That was parameter variation experiment. And that was useful. But ladies and gentlemen, within the parameter variation experiments, we needed to go through a little bit of a process because main was being brought into existence, run, and then disappearing. We needed to rescue some data from it every time. We sucked some data out of it, which we stored within the experiment, like in the histogram 2D. We sucked out the data from main before it was destroyed, and we summarized it in the experiment. We accumulated, maybe we added to a histogram, or maybe we put it in our histogram 2D data set. Now, when it came to calibration, the goal of calibration, the ostensible goal of calibration is to try to adjust model parameters to match observed data. One of the real additional, and I would argue maybe even more important goals of calibration is to learn from our model the degree to which it can really align with observed data, and to try to learn why it can't if it has difficulties, so that we can improve our understanding and so we can improve our model. And it turns out at a mechanical level it works very similar to the parameter variation experiment. Like a parameter variation experiment, a calibration experiment, or an optimization experiment, which is how we ran it, it runs the model many, many times, in this case for different values of parameters. And it's intelligent about trying to pick the values of the parameters so it gets better and better a match to the observed data. Now it doesn't always get better. It actually sometimes gets stuck at kind of a local situation where it can't get obviously better. So for a certain amount of time, it may tolerate getting worse so it can have a chance of discovering something better yet. So it's like it's trying to get down to the floor of a valley, and sometimes it's descending from the top of the mountain. It gets stuck at a little lake, and it's at the bottom of the lake. It can't get any better, so it has to come up and then go down again some other slope nearby. It's kind of like, it could come down here and get stuck here, and it's kind of flitting around here, and it's only by going up a little bit here then it can go down much further. Anyway, calibration involves optimization. It's optimizing parameter values so that the model best matches some observed data. But it's really an opportunity to learn. And there's a lot of experimentation you can do in learning that will clue you into why a model is or is not adequately accounting for patterns we see in the world. So it's one of the big points of learning. Now, so in the sense that both parameter variation experiment on the one hand and calibration on the other, both of them run the model many, many, many times. So they might run main 1,000 times, 100 times, and summarize the results from that. Now, to get to Joanne's question, is there a way to layer parameter variation and calibration? Why might you want to do that? Well, there's some very good reasons you might want to do that. Maybe what you want to do, for example, is vary assumptions about a parameter, and then for the varied assumptions about the parameter, you want to run a calibration, which, for the varied assumption about parameter A, you're going to calibrate B, C, and D so that it best matches the data and summarize the results. And unfortunately, I'm not aware of a built-in way in any logic to do that. Could you do it? Yes, you could, using a thing called the custom experiment in the professional version. So you could do that. It is a need that sometimes comes up, but I'm not aware of any way to layer them so that within each parameter variation experiment, each sort of changed alternative assumption about parameter A, you then run a calibration. I'm not aware of any way to do that. If any of the TAs are aware of a way, I would welcome it. But
can you say it again exactly what the goal is?
Sure.
To be fair though, that's quite a little bit more complicated than what I was asking. But I was just asking, could you optimize the parameters?
In the parameter variation experiment.
Well, like when you run, when you optimize when you calibrate,
Yep.
you're calibrating to a specific goal, right? So you're doing
Yep.
an optimization to a goal.
That's right.
But what if you just wanted to max it? Like then you just put in a
Oh
or
yeah.
max it or min it.
Sure.
Then I
sure.
suppose what you just put in an observed high flat value or
Yeah.
an observed low. Just pretend your observation is flat and high.
Yeah. So not positive I'm getting your question, but let me answer what you may be asking, because it's a very germane. And if I'm not addressing your question, you can further explain it. So one question is, sometimes calibration is a special type of optimization.
Yeah.
It's an optimization that seeks to minimize some discrepancy. In some ways, we've described discrepancy between model results on the one hand and observed data on the other. All right? And as I argued that it's not always a matter of point matching and so on, and there's different ways to define discrepancy with deal statistics to capture trends and not just point matches or whatever. But fundamentally, calibration is a type of optimization with the goal of matching up some features of empirical data. Maybe what you're asking is, can you use that same mechanism to optimize parameters for other goals? For example, could you optimize parameters so that an intervention is maximally effective? For example, the parameters represent assumptions about the character of that intervention, and we want to tweak them so that they yield the biggest bang for the buck from the intervention, or something like that. And the answer absolutely is yes. And it's through the optimization experiment in any logic, you could do that. So the objective function, the function that specifies the discrepancy or specifies the badness of the current match, you could define it in a way that takes into account the gain of a policy. You'd probably do it minus the gain of the policy, or you try to minimize the health burden that results. And by adjusting the parameter values, you'd be trying to find assumptions about intervention design that would minimize the health burdens in the population following that intervention. Is that helpful?
Yeah.
Okay. So yeah, that's good. So that was calibration. I noted calibration is a big topic. It's one you'll find me talking about online, and I think it's one that it's a key point for learning. Okay, so that's my bit of retrospective. Any questions before we go into model conceptualization discussion? Yes.
Just one thing, when you're running the same model with the same parameters, and you're just trying to measure your stochastic variation.
Yeah.
Is there a way of deciding what seeds are used in your actual ones just so that you can rerun exactly the same.
Yeah, there is. Thank you very much for asking. Okay, so this gets into some issues in health economics practice as well, et cetera, where we want to have very tight control over certain types of things. So I've been approached by several health economists, I believe, about designing experiments using any logic where parameter values are, say, drawn from, in a Monte Carlo fashion from distributions, but you want to use the same value of the randomly drawn parameter value for the baseline and the alternative case, the intervention case. And you can do that in any logic, and you can also do what you just described, which would be using specified seed values, so you know it's completely reproducible, in short. And the way you do it, so I have a quite clear conceptualization of how you could do it. What I can't promise you is that the sort of most elegant way to do it. What people of Kurt and Dylan's generation will call slick. Is it the most elegant way to do it? I'm not sure, but what you can do with confidence is you can use within any logic's mechanisms what are called custom random number generators, and so you could basically initialize it with a seed of your choice. Maybe you read it from an Excel sheet, or you read it from a database, or whatever. You read it from a file, and you then use those seeds in successive runs. And so there, you're not leaving it up to any logic to decide. You're dictating this. And one of the options in any logic, which you may have noticed, and I'll go over here to any logic. We want to do this. We want to go look at our. This is going to be a problem here. I can't really read what's going on the screen there, so I'm at a disadvantage. Okay, so let me just load in a model here. Hey, come on. Hey, oh man. Hey, what's going on? Oh man. Okay, yeah, this is probably not going to be a viable option for me, but here we go. This is, I think, the health economics model. I need a pair of binoculars.
Would be easy if you set that.
Oh, sat like there?
Yeah, set there.
That is a fine idea.
Alternatively, Nate, I bet you if I gave you my laptop, it would work.
Yeah, but I want to do it. Yeah. I have it all set up to upload things and so on. So.
Nate, could you write like Java code so that you're thinking that you just so like plus the C, so like
Yep. You could.
and that way you can just exactly what C.
That's right. Yeah. Here we go. So, ladies and gentlemen, so if you go down to the random seed, you see there's three choices here. And again, I need a pair of binoculars. But the first one, I think, is randomly used. And this one will pick a random seed for you. The next one down is fixed seed. And then the third is custom generator. And so you could use a custom generator. Now, we also have mechanisms that will allow it to override the seeds that it assigns automatically. So we can inject seeds into it, say, use this seed instead, buddy. And we'll do our bidding. And that's a somewhat more advanced technique. But the long and short answer is that there are several ways to do it. Okay? There's several mechanisms for doing it. So absolutely. Any other questions right now before we get into model conceptualization? Okay? Great. Okay. Maybe what I will do here, let's just see. Okay, we're gonna have layout issues. Okay, let's continue to kind of do this, and we will switch over. Okay, yeah, no, we don't want that. We want to go here. Hey, come on. Okay. Yeah, this is not viable. Okay, sorry folks, I'm going to switch to a lower resolution and bring it back to my computer so I can actually see what's going on. Forgive me, I've been doing these boot camps for a while, but doing them blind is not yet an option. Okay, other point, I believe I would have a fitting colleague in Jeff to challenge me. Okay, so here we go. Okay, now we're in good shape. Okay, now we're back to a sane world. Okay, so ladies and gentlemen, we're going to go down here, and I'm going to stop this recording.